These days, we are awash in data, maybe more data than we can handle. So compressing data where possible can be very important. For instance, picture files can be very large, and a website with many pictures will load very slowly if we don't control the size of the files. But digital files are just data, and the key idea in digital compression is that when such files do not span the entire space of possible data, there may be more efficient ways of storing data than the matter in which they normally arise. For instance, if your file is text, each letter may be stored in your data file as one 8-bit string of zeros and ones, like 01000001. There are 256 such strings, but only about 30 different characters that are used for each letter of a text file. So some 8-bit strings are never used, and that's a lot of wasted space. Wouldn't it be nice if we could store the information more efficiently? Another example is image files. You may know that since 1992, many digital pictures are stored in a compressed format known as JPEG. There are many ideas behind JPEG compression, but one is the conversion of information using something called a discrete cosine transform. The basic idea here is to break a photo into 8x8 blocks of pixels. Nearby pixels tend to have similar color and light intensity. So real images do not have 8x8 blocks that span the entire 64-dimensional space of possibilities. If we can choose a good set of vectors that span the possibilities, then the associated coefficients will be nice in the sense that there will be very few big coefficients. Then if you store only the big coefficients, that may be good enough to reconstruct a good approximation of the image. Let's do a very simple example. Suppose I have a one-dimensional image file saved as a vector of light intensities. This is an image file where the light intensities vary quite smoothly. One way to compress this data is to take advantage of the fact that nearby pixels don't change very much. So if I break the file of 10 pixels into pairs, you'll notice that the pairs can be thought of as points x, y in R2. But they all lie very near or on the diagonal subspace where y equals x. In other words, near multiples of the vector 1, 1. A very crude data compression scheme could just choose to represent each pair as a linear combination of two vectors, 1, 1 and 1, minus 1. Then, do you see that in this new set of vectors, which we will call a basis, that all these pairs of points have one large coefficient, the coefficient of 1, 1. If you throw the other coefficient away, then that is just 5 numbers to remember rather than 10. The resulting image will now have these light intensities. Although we've lost some information from the original, this is what's called lossy compression, the image remains very close to the original, and this data size here is half the size of the original file, involving 5 numbers rather than 10. Now the idea of JPEG compression builds on this idea, except that the block size is not pairs, but 8x8 grids. And the basis is not two-dimensional vectors that span a two-dimensional subspace, but a larger set of good vectors that span a 64-dimensional space. Real images will have 8x8 blocks that stay close to a subspace of that 64-dimensional space. So you can throw away some of the coefficients without losing too much information. So what do we want from what we're calling a basis, this good set of vectors? Well, the first thing is that we want the good set of vectors to span the space we're interested in. The second is that we want them to be linearly independent, so there isn't redundancy in how we express the vectors. There's only one way to write any vector as a linear combination of those vectors. That's the property we want. It's also useful to have some of the vectors span the subspace where interesting things occur, so that coefficients of the other basis vectors are small. So that's the subject of this lecture. What do we mean by a basis, and how do we find a basis for a subspace? Last time we learned about special subspaces associated with a matrix, the row, column, and null spaces associated with the matrix A. Since most subspaces we care about arise as subspaces of these kinds, let's now try to understand what these spaces represent geometrically. Recall that every m by n matrix A represents a linear transformation in the following way. Let the function t of x be defined to be A times x. Then t is a linear transformation from Rn to Rm. In effect, t is the function that performs matrix multiplication by A. But we've also seen that A times x can be viewed as a linear combination of the columns of A. But this means that the range of t, which is the set of all possible vectors that result from multiplying A by some x, is the same as the set of all linear combinations of the columns of A, which we learned last time is called the column space of A. So the column space of A has a natural geometric interpretation as the range of the linear transformation arising from multiplication by A. This column space could be all of Rm, but it could also be a smaller subspace of Rm. Besides the range, another important object associated with the linear transformation t of x equals ax is its kernel. The kernel of t is the set of all vectors in the domain of t that map to 0. So the kernel of t is just the null space of the matrix A, because it is a set of all x for which A times x is 0. We saw last time that the null space of A is a subspace of Rn, the domain of t. Both the kernel and the range of a linear transformation are important because many subspaces we care about arise as kernels or ranges of some linear transformation. For instance, a solution set to a homogeneous system of equations, Ax equals 0, is the kernel of the linear transformation t of x equals A times x. The span of any set of vectors is the range of the linear transformation t of x equals A times x, where the vectors are the columns of the matrix A. Let's display a picture that might suggest what is going on. A linear transformation represented by A takes Rn to Rm. Here I've drawn both Rn and Rm as planes, but this picture is just meant to guide your intuition. The null space, indicated here in yellow on the left picture, lives in Rn, and it is the kernel of the linear transformation t of x equals ax. Multiplication by A takes everything on the yellow line on the left and maps it to the origin, the yellow dot in the right picture. Also, the entire picture on the left, representing all of Rn, gets mapped to the blue line on the right, which is the range of the linear transformation t. What about row A, the row space of A? Well, I claim that any vector in row A is orthogonal to any vector of null A. So in the picture, the row space of A in green on the left are the vectors perpendicular to null A in yellow. We can see why vectors in row A are perpendicular to vectors in null A by using our earlier observation that a 1 by m row vector Q times an m by n matrix A is a row vector that is a linear combination of the rows of A. So if x is a vector in null A, then QA times x is, by associativity of matrix multiplication, the same as Q times AX. But since x is a null A, we have AX equals 0. So Q times A times x equals 0 as well. This means the quantity Q times A, which can represent any vector in row A, must be orthogonal to any vector x in null A. If you drew enough pictures like this, you would notice some interesting geometric relationships between these subspaces. For instance, the dimension of the row space and the column space are the same, even though they live in completely different spaces. The row space lives in the domain, and the column space in the codomain of the transformation T of x equals ax. We shall see why by defining the notion of dimension carefully. To do so, we need the notion of a basis. As we have seen, every subspace is the span of a set of vectors. Recall that one way to think about the span of a set of vectors in Rn is to think of a spaceship at the origin, and the vectors are the set of thrusters that you can fire to move in various directions. Then the span of those vectors is all the places you can go using those thrusters. This will be a subspace of Rn, but it may or may not be all of Rn. And if I were designing this spaceship, I might try to be as economical and use as few thrusters as possible. So if I don't need all the vector thrusters, I might get rid of some of them. Intuitively speaking, a basis of vectors for a subspace is a minimal set of thrusters that I might need to reach all the points in that subspace. Formally, we say a basis B for a subspace H is a set of vectors such that two properties hold. First, the vectors must span H, and second, the set B must be a linearly independent set. The first condition ensures that your thrusters can reach all of the subspace H. The second condition says that you have no redundancies. Recall, to be linearly independent means that there is no non-trivial linear combination of the vectors in B that will produce a zero vector. We showed that this was equivalent to saying that no vector in B can be written in terms of the others. So removing any thruster from your set means you won't be able to reach all of H. Let's look at some examples. The first example is R3, which is a subspace of itself. There's a very natural basis called the standard basis for R3. This basis is a set of three vectors that point along the coordinate axes and are unit length: 1, 0, 0, 0, 1, 0, and 0, 0, 1. In math, we often denote the standard basis using the letter E with a subscript, like E1, E2, E3. The physics community often uses different symbols, I hat, J hat, K hat, for these three vectors. Using the standard basis, writing any other vector as a linear combination of these vectors is, in some sense, what you already do when you specify coordinates. For instance, the vector 3 minus 1, 4 really means 3 times 1, 0, 0, plus minus 1 times 0, 1, 0, plus 4 times 0, 0, 1, or 3i minus j plus 4k if you were a physicist. From this example, it is easy to convince yourself any vector in R3 is a linear combination of the standard basis vectors. So they span all of R3. And the vectors are linearly independent because if you remove any one of them, you won't be able to get all the vectors in R3. For instance, if you remove E2, you won't be able to get any vector whose second component is non-zero. But R3 has other bases. For instance, look at 1, 0, 0, 1, 1, 0, and 1, 1, 1. For simplicity, label them V1, V2, and V3. You can check that these vectors form a basis for R3 by noting that the matrix A, with these vectors as columns, is already in row echelon form. And since there is no row of zeros, the linear system AX equals B can always be solved, which means the column vectors span R3. Also, the linear system X equals 0 has no free variables. So Ax equals 0 has a unique solution, which must be the trivial solution. So the columns of A must be linearly independent. The vector 3, minus 1, 4 can be written in terms of these vectors, v1, v2, v3, by solving ax equals 3 minus 1, 4. You will find 3 minus 1, 4 equals 4 times v1 minus 5 times v2 plus 4 times v3. That's a linear combination. Okay, so why are bases important? Well, aside from giving you a basic set that you can use to build all other vectors in your subspace, another important reason is that there is only one way to build a vector as a linear combination of a given basis of vectors. We can state this as a theorem. Every vector v in a subspace H can be expressed as a linear combination of given basis vectors, and it can be done in only one way. So for instance, 3i minus j plus 4k cannot be equal to 7i plus 2j plus 3k. Unique representations means that vectors that look different really must be different. That wouldn't necessarily be true if the basis vectors were not linearly independent. And this insight helps us see how to prove the theorem. In mathematics, when one wants to show that there's only one way to do something, we often start by assuming that there were two ways to do that thing, and then show that those two ways were really the same. So let's start our proof. Say B is the set of vectors v1 through vk, and suppose it's a basis. Suppose that there are two ways to write a vector w in terms of that basis. First as a1v1 plus akvk, and second as b1v1 plus bkvk. Now, if I subtract one equation from the other, I will see that the 0 vector equals a linear combination of v1 through vk with coefficients quantity a1 minus b1 through quantity ak minus bk. But here's where linear independence comes in. Because b is linearly independent, all these coefficients, ai minus bi, must be 0. So ai equals bi for all I, which shows that the two ways of expressing w was really the same way. End of proof. So we've proved that a basis for a subspace allows us to express any vector in the subspace uniquely as a linear combination of the vectors in the basis. The coefficients of this combination are called weights, or coordinates, with respect to b, the basis. So for example, the coordinates of 3, minus 1, 4, with respect to v1, v2, v3 earlier, are 4, minus 5, and 4. These coordinates are basically telling me how much to fire my rocket thrusters in particular directions. Any other basis will produce coordinates with respect to a different set of thrusters. So, a subspace can have many different bases. But it is a fact, which we won't prove here, that any two bases for a subspace H must have the same number of vectors. Because the number is independent of the basis chosen, we can call that number in the basis, number of basis elements, the dimension of the subspace H, denoted by dim H. It tells me how many degrees of freedom, so to speak, my subspace H has. So if the subspace H has 1 degree of freedom, for example, choice of a coordinate, we'll call it a line. If it has 2 degrees of freedom, choices for coordinates, we'll call it a plane, etc. So if you want to find a basis for a subspace that is a span of a set of vectors, then you could just put those vectors in the column of a matrix, and then you are basically changing the problem to finding a basis for the column space of a matrix. And there's an easy way to find the basis for any column space by using, guess what? The reduced row echelon form of the matrix. For instance, Suppose my matrix A is a 4 by 5 matrix with entries 1 through 19, like this, and a stray 21 in the last entry. We'll call the columns C1 through C5. Now, if we do row operations to get the RREF that we see here, and after we've done that, call those columns C1 prime through C5 prime, then we can look at all the columns of the RREF that have a leading 1. These are the so-called pivot columns. In this case, it's the first, second, and fifth columns, C1 prime, C2 prime, and C5 prime. This tells me which of the original columns will form a basis for the column space of A. In this case, C1, C2, C5 are a basis. That is, the vectors 1, 6, 11, 16, 2, 7, 12, 17, and 5, 10, 15, 21 are a basis for the span of all 5 columns. The span must be a 3-dimensional subspace of R4. Now, why does this curious method work? Well, the key idea is that doing row operations does not change the linear dependencies among the columns. So if some linear combination of the CI's equals 0, then the same linear combination of the CI primes will equal 0 too. For instance, you can check that C1 minus 2C2 plus C3 equals the 0 vector. So then, C1 prime minus 2C2 prime plus C3 prime equals the 0 vector as well. This also means that if, in the RREF, the first, second, and fifth columns are linearly independent, then in the original matrix, the first, second, and fifth columns are linearly independent as well. Because whatever coefficients worked for C1 prime, C2 prime, and C5 prime to get the 0 vector, namely, only the 0 coefficients did, those same coefficients are the only ones that work for C1, C2, and C5. Thus, we see how to find a basis for a column space of a matrix. And the nice thing about it is, this method produces a basis consisting of vectors from the original spanning set. It just potentially throws away some columns that weren't necessary. In this case, C3 and C4 could be thrown away. Now, how do you find a basis for the row space of a matrix A? Well, you can also use the RREF of the matrix A to find this as well. Just look at the non-zero rows of the RREF. That's it. That's a basis for the row space of A. In our example, you can see that the first 3 rows of the RREF are non-zero vectors. These are a basis for the subspace spanned by the rows of A. And unlike the column space method we just learned, the row space basis produced by this method does not use the original vectors of the spanning set of rows. It finds some new vectors. So in our example, a row space basis is 1, 0, minus 1, minus 2, 0, and 0, 1, 2, 3, 0, and 0, 0, 0, 0, 1. It is a 3-dimensional subspace of R5. This method works for a different reason than the column space method. Doing elementary row operations by their very nature does not change the row space of a matrix. This is because a row operation produces a new row that's a linear combination of old rows. And since elementary row operations are reversible, the reverse is true too. What we see in the RREF is that the 3 non-zero rows clearly span the row space, and they're linearly independent because of the echelon form. Finally, what about finding a basis for a null space? This means finding solutions to the homogeneous system AX equals 0. And we've actually already done this before. Recall that we form the augmented matrix A with a column of zeros and then row reduce to reduced row echelon form. This enables us to figure out which are the free variables by looking at columns without leading ones. Then we express all other variables in terms of the free variables using the RREF just as we learned to do before. In our running example, the free variables are x3 and x4, since they do not have leading ones in the corresponding columns. We then get x1, x2, x3, x4, x5 in terms of x3 and x4 as x3 times the vector 1 minus 2, 1, 0, 0, plus x4 times the vector 2 minus 3, 0, 1, 0. This shows the set of solutions is spanned by the two vectors 1 minus 2, 1, 0, 0 and 2 minus 3, 0, 1, 0. It turns out that the vectors you obtain in this way must also be linearly independent, because if you look at the third and fourth entries of the vectors, there is no way to produce the zero vector unless the coefficients of these two vectors is 0. The point here is that you already know how to find null spaces because you know how to solve linear equations using the RREF to find the null space as a span of some vectors. The nice thing is that the vectors you obtain in this way also turn out to be a basis. We conclude by looking at the dimensions of the row, column, and null spaces and making some geometric observations. Let's call the dimension of the row space of A the row rank of A. And let's call the dimension of the column space of A the column rank of A. In our example, both these numbers turned out to be the same number, 3. And this was no accident. Both of them are equal to the size of their bases, and both bases were derived by looking at the leading ones in the RREF. The column space basis consisted of columns of the original matrix, corresponding to leading ones in the RREF. The row space basis consisted of rows of the RREF, corresponding to leading ones. So the surprise is that the dimensions of the row space and column space will always be the same, even though those objects live in different spaces, Rn versus Rm. So we've just proved a theorem that the row rank and column rank of a matrix are the same. So we give this number a name. We simply call it the rank of a matrix A. The rank of a matrix A is the dimension of either its row space or its column space. Let's call the dimension of the null space of a matrix the nullity of A. We saw that this was equal to the number of free variables in the system of equations AX equals 0, which is the number of columns of the RREF that do not have a leading one. So this means that if you add the nullity to the number of columns with leading ones, you get the total number of columns. And for an n by n matrix, the number of columns is n. So this proves the rank nullity theorem, that the rank of A plus the nullity of A is the total number of columns of A, which is n. We can see these relationships now if we return to our picture. Here you see that the dimension of the row space of A plus the dimension of the null space of A must equal the dimension of the entire domain on the left, which is n. Also, the dimension of the row space of A is the same as the dimension of the column space of A, even though they are subspaces of different spaces. This is hidden structure that wasn't obvious at first glance, but it's now illuminated. In our next lecture, we'll put many of these ideas together to try to further understand the geometry of linear transformations, which are the basic objects of linear algebra that arise, as we've seen, in so many places.